Neural networks. Let me start with a question. How does your brain know that this is a cat? You do not measure the length of its ears, count its whiskers, or check every possible feature. You look at it and know almost instantly. Your brain recognizes a pattern. For decades, computer scientists tried to give computers that ability by writing rules. If it has fur, 4 legs, and pointy ears, call it a cat. But a dog can match those rules too. The real world is far too messy for humans to describe every pattern by hand. Then came a better idea. Instead of telling the computer every rule, let it discover the patterns from examples. That idea gave us neural networks. A neural network is a machine learning model made from layers of tiny mathematical units called neurons. It is loosely inspired by the brain, but it is not a digital brain. It is a pattern learning machine. Now, to understand neural networks, picture these 3 stages. The input layer receives raw information, such as the pixels of an image. Hidden layers transform that information into increasingly useful patterns. Finally, the output layer produces a prediction, such as, this image is 95% likely to contain a cat. Inside each neuron, the mathematics is surprisingly simple. It multiplies its inputs by numbers called weights, adds a bias, and passes the result through an activation function. Think of weights as volume knobs that control which signals matter. The bias shifts the neuron's threshold, while the activation function decides how strongly the result moves forward. One neuron can do almost nothing, but if you stack thousands or millions of them across many layers, and something remarkable happens. In case of an image network, an early layer might detect edges. The next combines edges into shapes. Deeper layers recognize features such as eyes, ears, and whiskers. And the final layers combine those features into the concept of a cat. Nobody manually programs every detector. The network begins with mostly random weights and learns useful values from data. Collectively, those weights encode the patterns the model has discovered. The same foundation powers image recognition, fraud detection, language models, and transformers. Different architecture, but same basic ingredients. But an untrained network is only empty machinery. So how does it discover the right weights? And once it has them, how does it use them to answer us? Those are 2 completely different modes called training and inference. Okay, so we have built the brain, a neural network where layers of math are connected by weights. But here's the thing, at this stage, that network is empty. It doesn't know anything yet. So the question arises, how does this thing actually become useful? How can it answer your questions? And the answer is, a model has 2 completely different modes of operation, training and inference. To understand training and inference, let's consider this student analogy. Think about a student preparing for an exam. There are 2 phases in their life. First one, where they read books and solve practice questions. Over time, knowledge gets into their head. That's training. Then there's the exam day, where they get a question and answer it. No teacher correcting them, just produce the output. That's inference. A neural network works exactly like that. In training mode, you show millions of examples, like all that glitters. And the model has to predict is not gold. If it gets it wrong, you penalize it. The internal weights of the neural network update. The model is now slightly better than before. Do this billions of times, and you have something that actually knows things. On the other hand, inference is when the model is done learning. You ship the model and put it on a server. When a user hits your API with a query, your model just answers instantly. It doesn't update its weights anymore. It just uses what it already knows to predict the next token. They train once, then they serve that model to millions of users in inference mode. So remember this, training is when the model is learning. Inference is when the model is answering. Now, I've said the word token a few times already, but I never actually told you what a token is. So let's fix that. Here is an interesting thing about LLM. When you type, write a story about a robot exploring Mars, Claude does not receive one complete sentence. Before the model can process your request, a tokenizer cuts the text into smaller pieces called tokens, and tokens are not always complete words. Take the word unbelievable. You see one word, but depending on the tokenizer, the model might see 3 pieces, like yun, believe, and able. A common word like the may remain whole, while an unusual name or a long technical term might be divided into several tokens, spaces, punctuation marks, and even parts of emojis can become tokens too. But why does it chops language into pieces? Because an AI needs a manageable vocabulary. It cannot store every word that humans might ever invent. Instead, it learns smaller, reusable patterns. Consider the ending ing. It appears in running, writing, learning, and thousands of other words. By learning that piece once, the model can reuse the pattern across language, even in words it has rarely seen before. But here is the surprising part. The model never works directly with letters. After tokenization, every token receives a numerical ID. Imagine cat is number 8,241, while kitten is number 17,903. Those numbers are not definitions. They are simply labels like barcodes on products. Your prompt becomes a sequence of numbers, and the neural network performs math on their representations to predict which token should come next. Embeddings. A tokenizer turns text into tokens, but tokens are only labels. If cat is number 8,241, that number does not tell the model that cats and kittens are related. So, where does meaning come from? The meaning comes from embeddings. Imagine a map with an x-axis and a y-axis. Place cat at one point. Put kitten and dog nearby because they are related. Then place airplane far away. We have turned words into coordinates, where similar ideas sit closer together. An embedding does the same thing, but instead of two coordinates, it represents each token using a long list of numbers called a vector. Modern models use hundreds or even thousands of dimensions. We cannot visualize them, but the mathematics still works. During training, the model adjusts these vectors. Tokens used in similar contexts gradually develop related positions. Now the model can compare meaning by measuring distance. For example, a search for repair a dripping tap can find an article called How to Fix a Leaky Faucet, even though the wording is different. Embeddings can also capture relationships. In a classic example, take the vector for king, subtract man, and then add woman. The result often lands near queen. Similarly, Paris minus France plus Italy can land near Rome. These equations are useful illustrations, not perfect laws, but they reveal something powerful. Geometry can represent relationships between ideas. Modern language models go even further by making these representations contextual. The word bank changes depending on whether the sentence refers to money or the side of a river. This idea powers semantic search, recommendation systems, retrieval augmented generation, and vector databases. A vector database stores embeddings and quickly retrieves the closest matches. So, embeddings are the bridge between tokens and meaning. They turn simple ID into mathematical representations that a model can compare, connect, and understand. So, a traditional embedding gives that word only one fixed coordinate, one point on the map for two completely different meanings. So how can a model determine which meaning you intended? The missing ingredient is context. The model needs a way for every word to examine the words around it and decide which ones are important. Researchers had explored this idea before, but in 2017, a team at Google made it the foundation of a revolutionary new architecture, the transformer. The mechanism at its center was called the attention mechanism. Attention is the idea that changed how AI handles language. A basic embedding gives each token a starting vector. One fixed vector cannot capture every meaning by itself. The solution is context. Consider this sentence. To open the file, I click the mouse. Does mouse mean an animal or a computer device? With self-attention, the model compares mouse with the other tokens and asks, which words are most useful for interpreting this one? Open, file, and clicked receive high attention scores. These scores work like volume controls. Relevant information is turned up, while less useful information is turned down. The model combines those signals to create a new, context-aware representation of mouse. In this sentence, it moves closer to concepts like keyboard and computer, rather than cheese and animal. Now change the sentence. The hungry cat chased the mouse. Attention connects mouse with cat and chased. Same token, but the context and representation is different. This process happens throughout the entire sequence. Models can also use several attention heads at once. Different heads can capture different relationships, like it could be an action or a pronoun, and the noun it refers to. Stack many attention layers together, and the model builds an increasingly rich picture of how the sentence fits together. Now, here is one important historical correction. Attention was not invented in 2017. It had already existed for several years. The breakthrough came when Google researchers published a paper called "Attention is All You Need." They introduced the transformer, an architecture that placed self-attention at the center of the model. Instead of processing words one by one, the transformer could examine many relationships at the same time, even between words far apart in a passage. That made training faster, more scalable, and ultimately changed the direction of modern AI. ChatGPT, Claude, Gemini, and most modern language models descend from this design, but attention is only the mechanism. It still needs a complete architecture to organize these calculations across layers and turn them into a working model. That architecture is the transformer. And no, we are not talking about Optimus Prime. This transformer is the architecture that reshaped artificial intelligence. First, let's clear up a common confusion. A large language model and a transformer are not the same thing. An LLM is a trained model designed to process and generate language. A transformer is the architecture used to build it, or a transformer is the blueprint for how information moves. Think of LLM as the finished car and the transformer as its engine design. So, how does the transformer actually work? First, your prompt is divided into tokens. Each token becomes an embedding vector. The model also adds positional information so it knows the order of those tokens. Otherwise, dog bites man and man bites dog would contain the same pieces. Those vectors then enter a stack of transformer blocks. Each block has two main stages. First comes self-attention. During text generation, every token measures how relevant the earlier tokens are. This helps the model connect pronouns to nouns, resolve ambiguous words, and follow relationships across long passages. Next comes a feed-forward neural network. Attention gathers useful information from the context. The feed-forward network processes that information at each position, creating richer patterns and representations. Residual connections help preserve earlier information, while normalization keeps the calculation stable. Then, the same pattern repeats. Attention, feed-forward network, attention, feed-forward network, layer after layer. The layers do not have fixed jobs, but as information travels deeper, its representation becomes more refined, from basic words and grammar to relationships, tone, and instructions. After the final layer, the model assigns a score to every possible next token. One token is selected and added to the sequence. Then the process continues. Token by token, a complete response appears. That is a transformer, which is a repeating architecture that turns token vectors into context-aware predictions. But there's one important limitation. Attention cannot look back forever. It can only use the tokens the model is allowed to keep in view. Your prompt, conversation history, reference material, and the model's own response must all fit inside that limited space. That space determines how much information the model can consider at one time. It is called the context window. Transformers are powerful because attention lets tokens use information from other tokens. But that ability comes with a cost. In standard self-attention, every token compares itself with every other token it is allowed to examine. With 10 tokens, that can mean roughly 100 comparisons. With 1,000, it becomes around 1 million. If you double the input length, and the attention work can grow by about 4 times. Longer inputs require more memory and more computing power, as well as more time. That cost is one reason every model has a boundary where it only can process a certain number of tokens together. This boundary is called the context window. Think of it as the model's working desk. Your prompt, conversation history, reference documents, and the model's response all need space on that desk. When the desk becomes full, the application must reject the extra text, automatically compact the context, or remove older tokens. Once information leaves the active window, the model cannot directly use it. And here is the thing. A larger context window does not guarantee perfect recall. An important detail can still become buried inside thousands of pages. Processing unnecessary tokens also costs time and money. This becomes a serious problem in real applications. For example, a customer support assistant might need thousands of pages of company policies. A coding assistant might need a codebase far larger than its available window. Pasting everything into the prompt would be slow, expensive, and sometimes impossible. A better approach is to retrieve only the information needed for the current question. That technique is called Retrieval Augmented Generation, or RAG. We will return to it later. For now, remember this. The context window defines how much information a model can actively consider at one time. But it also reveals a much bigger lesson. In AI, increasing scale brings greater capability, but also greater cost. So what happens when we scale the model's training data and its computing power together? The answer leads us to the scaling laws. For years, AI progress seemed to depend on inventing cleverer algorithms. Then, researchers found another powerful lever: scale. When transformer models were trained using different numbers of parameters, different amounts of data, and different levels of computing power, their improvement followed a surprisingly smooth pattern. Scale those three ingredients in the right balance, and the model's error falls predictably. These relationships are called neural scaling laws, and that word, predictably, is crucial. By testing smaller models, researchers can estimate how a much larger model may perform before spending millions to train it. But scaling is not only about adding more GPU and the intelligence appears. Data quality, architecture, and optimization still matter. A giant model trained on too little data can waste computing power.